Hello everyone. I'm Sai Surya Nattuva, and my project is basically classifying human activity from a time series data. So why I chose this project is because so there are a lot of sensors that can track human activity, like the Apple Watch or pedometers or step counters and other kind of stuff. And by analyzing and making use of machine learning models on this kind of data can result in a lot of technologies like the fall detection, irregular heart rhythms, logging steadiness, etc. So for this project, the data that I've used is from an accelerometer of a user smartphone. So we are like the smartphone has an accelerometer which gives us the x, y, and z axis, right? So I've like taken that data, and so the activity that I've tested this on is one of my friend was practicing boxing. So he held the phone in his dominant arm and he was just like practicing. So the data generated by the phone is in the form of a time series data, and I have like four features from that data. That's the x, y, z axis, and also the g force meter with how the power that he is using. And so to build the model to do the classification task, I've used a published state of the art neural network architecture called SensorNet. So so I'll just go about that. So first, coming to the data that I've created. I've used a specific like I try to capture the data by using Android activities, but there is this one app called Physics Sensor Suite Pro or something. So what it does is you can start a recording session in that. You can just take the gyroscope screen of that, and it just keeps recording, and you can do it. And once the recording session is done, it will export the data into a CSV format along with the timestamps and the other four features. um, so as you can see in the graph here, so since the app does not label the data for me, so I had to come up with another solution for that. And for that I used open source tool called Label Studio. So what that does is, as you can see, it just gives out all my sensor values on the line, and I can just like simply select this label and just drag the regions that I want to label them as. And so based on this gives me annotations on the data. And so then I had to pre-process those annotations along with my data to label each and every data point. So coming to the pipeline, as I said, I have adapted this model from the SensorNet neural network architecture. So what this basically does is, so this is specifically made to classify time series which has multiple modalities. That is, so in my case I have four modalities. That's the axis and the g-force features. So as you can see, the raw time series data is and since this is like built using a deep neural convolutional neural network, we are going to I converted the data into time series images by transposing the data and taking windows of the data of size 64. And I chose 64 because my polling rate for the sensor was around 100 hertz. And I had recorded like multiple sessions of the practice, multiple sessions of the training, but I was able to get like good data for about over 100 seconds. So as you can see, the first pre-processing step is just converting the time series data into images, and then it's going to it is passed into the neural network architecture, and then we predict the classes. If you can see down here, so this is the configuration of the neural network. So it has 5 convolutional layers with 3 max pool layers after the second, fourth, and the fifth convolutional layers, and then the fully connected 64 node dense layer and the output softmax layer. And I'm going to talk a little bit about why I went with this. So in the research paper, the implementation of the SensorNet, so the authors of this architecture used it specifically to gain very high accuracy by using very less number of modalities in the data. And also they have fine-tuned this network to be very computationally inexpensive, so it can process a lot of data like pretty quickly by reducing the number of computations within the layers. And so now coming to the how I split my data to fine tune the model and to the predictions is, so I was able to make 330 images out of this 100 plus seconds of training, the data set. And the window size is 4x64, and 4 is because it has 4 modalities. And I chose the training size to be 55% because as you can see from the graphs on the right, so I have a couple of moves that are like very few, so this data is also class imbalanced. And so SensorNet was also very useful in detecting the classes, even though even though the data is heavily class imbalanced. Yeah, so now coming to the hyperparameter tuning, so I've before doing the tuning, I have done some manual testing on like just ran a couple of codes to just to get an idea of how I can improve the SensorNet architecture to my needs so that it performs well in my task. And so this is the broad parameter grid that I've used, and I've used the randomized search CV to tune the hyperparameters for that neural network. So as you can see, I've tuned the number of filters, activation functions, epochs, batch size, and the optimizer, loss function, and the learning rates. And then I made a couple of plots just to see how good my model, the hyperparameters are being tuned. And as you can see, the number of filters, so from the tuned parameters, so we can see that the best number of filters I've chosen is 64. And so one more advantage of this architecture is that it really converges very fast. So the loss was almost negligible right after around 60 to 70 epochs. So, but 150 gave the perfect, like a very good accuracy in my case. And coming to the model performance, so these graphs, I mean, the accuracy plots I've made are based on the optimized parameters. So as you can see, I've plotted the ROC and AUC curves, and I also used the F1 score to evaluate the model's performance. And you can see here that the micro average ROC curve is 95%, that the model is 95% accurate in classifying the activities, and the F1 score is 84%. But one place where my model really struggle is the cross and the jab. And as I said, so my data set is really class imbalanced. So there were a very less instances for the cross and the jab moves. But still, it didn't do a very good job, but it was able to identify them in most of the cases. So yes, and this is the paper that I've referred to build the neural network. And thank you.
I have a question for you.
Yes,
can you demonstrate the difference between a cross and a jab, like literally physically demonstrated?
So I mean,
I wonder why would the network be so bad at it
in detecting those two?
Yeah.
So I mean, so the training session was done by my friend, so I'm just going to try and see what it was. So the way he did was, a cross is kind of like a straight punch.
Okay.
And the jab was kind of extending the arm. So
Very similar movement.
yeah. Oh yeah, I might have got it confused. Sorry. Yeah. So the jab was straight, but the cross was kind of like to the cheek. Yeah.
Okay.
I mean, I used his help in labeling the data. So.
Okay. And another question, you mentioned something that your data set wasn't rich enough on crosses and jabs. Did I misunderstand, or was this the case?
No, this was the case. So, so as you can see here, so there's very less number of crosses and jabs, but I think that the model did not perform well for the jabs and the crosses because so the cross and jab are pretty close. Like if you look at the action or the movement of that action. So I believe that that is why the model, kind of suffered in classifying a cross and a jab.
Okay. And can you go again to the input data to your CNN? Right. So the time series image that you're showing,
Yes.
is it literally this dense, or is
No. This is just a representation. That's it.
Can you show an input image really quickly, or do you not have that?
So basically, image, as in I was just trying to convert the raw, like this sequential kind of time series data into windows of 2D kind of representation of the data.
Mm-hmm.
That image.
No.
The image on there, not the thing on the left.
Yeah,
So
but
that's what your data is.
yes. I mean, as I said, so like Ben showed you, like there are no real images in my case. So it is just like a windowing function which just, windows the time series into chunks.
Right. And what is your window of the image? Like you have a literally a signal that goes through.
Yeah.
How many seconds or minutes do you cut per image?
So like my data is polled at 100 hertz, so I have about 100 or 1 or 2 data points for a second of data.
Okay.
So my window size is 64. I took 64 because like when I was labeling the data, I kind of eyeballed it that each punch takes about a second, like to complete a move.
And these are not overlapping windows, are they?
They do actually overlap by 32, so exactly half. So my window size is 32, but the step size is my window size is 64, but the step size is 32.
Okay, thank you.
They actually use it for boxing statistics. I mean, in the sense that, yeah, of course that, like Gillian White, for example, didn't care about Jack over as long as they're going down. Right? But did they ever use it in real, maybe for boxing statistics? Because sometimes it's probably useful for a jury also.
Yeah.
And also for people who try to
I mean,
measure boxing statistics.
so Professor Gokhan Kul's original idea was like to make a anomaly detection system from a time series data kind of. So we would train the model on the known states and we would tweak the softmax layer to kind of, introduce bias or get the probabilities and define a state as anomalous. But yeah, I think we can extend this program, like this kind of architecture to, as you said, analyzing the boxing patterns or anything.
Any other questions?
No.